presentation?
No, ma'am. I think it's coming now, ma'am.
11B, okay. 11B, it's duty of all other students, not only few students who are always listening, whatever is being stated by teachers. Why not others? Should I call? If I keep calling you people, then I'm wasting my time.
Ma'am, before you begin, ma'am, Abhishek, Nabil, Zuhair, Kavin, Samuel, and Johan.
Okay.
They are there with they're there meeting with Bindu Manoj Kumar, ma'am.
Fine, fine. It's okay. When they let them come. So others, please switch on your cameras because 11B is hesitating. That's what we are getting it from other teachers. Anyway, did you see the? Can you see the slide presentation, boys?
Yes, ma'am.
What was the last thing we were doing?
Work done in an isothermal process.
Okay, work done in an isothermal process. Because once again, you should know what do you mean by an isothermal process. Let us go back for it. Again, I'll just
Ma'am, you explained it with the diagram. If you go to the previous slide, you'll see the pointers here that you did not show on you. You explained it too.
Now, once again, I'll just go back to that. See, in physics, a thermodynamic system, whenever you learn about thermodynamics, right? When you learn about thermodynamics, you learn basically the thermodynamical process taking place in a system. So in terms of physics, a conducting, if I can say, a conducting piston cylinder arrangement or cylinder piston arrangement, this piston should be frictionless plus a working substance. Your working substance, sorry, boss. Working substance, basically it is a gaseous substance, any gaseous material, because thermodynamics also almost related for heat engines which are used in automobiles as well as refrigerators, right? Your thermodynamics in physics is always related to, most of the time, the practical application is your heat engines and refrigerators. So if at all, if you think of your heat engines, this is how the cylinder piston arrangement, even for the brake system, you have cylinder piston arrangement that comes under hydraulics. But for thermodynamics, your heat engine basically consists of a cylinder piston arrangement where the piston is capable of moving throughout the cylinder, and there is a working substance where you can do work on the substance or the substance can do a work on the piston. Now, what is an isothermal process? Now, the system, especially the working substance, might be at a pressure P and might be at initial volume V, temperature T. These are called thermodynamic variables. Right? Whatever you learn right now in physics, we are dealing only with three thermodynamic variables: pressure, volume, and temperature. Right, boss? Now, suppose we have to check for your isothermal process. In case if I am supplying heat energy, if I am supplying heat energy to the working substance, that is your gaseous substance. Now what happens when the gaseous substance absorbs heat energy? The gas is it begins to expand. On expansion, right, when your working substance undergoes expansion, now the temperature of the working substance will decrease. But for an isothermal, you are talking about isothermal process. When you're talking about isothermal process, what happens? The working substance on absorbing heat energy, you are supplying heat energy to the working substance, so it absorbs heat energy, it undergoes expansion. When it undergoes expansion, its pressure and volume changes, but the temperature should not change. Your temperature should remain a constant. Why the temperature? How can the temperature remain a constant? What makes the temperature to remain a constant? So when it expands, naturally it loses heat energy, so its temperature will come down. To compensate this, the cylinder is perfectly conducting to the surrounding so that this gaseous material will absorb heat energy from the surrounding. This gaseous substance will absorb heat energy from the surrounding so that there will be, though there is a drop in temperature, the temperature now will remain the same. So this is how in an isothermal process, when you're compressing, suppose if you're compressing the gaseous substance, we were talking about expansion. When the gases expand, right, cooling takes place. So when the cooling takes place, there's a drop in temperature. 1 second, boys. Yes, sir. So two things that can happen in a thermodynamical process. One is the expansion, the other one is compression. So you're talking about isothermal process. In an isothermal process, if at all there is an expansion, right? Naturally, the temperature of the working substance comes down. So to keep the temperature constant, because isothermal process is nothing but where your pressure and volume changes but temperature remains a constant, the working substance absorbs heat energy from the surrounding. Hence, the cylinder should be perfect, even the piston for that matter, should be perfectly conducting to the surrounding. This is in case of expansion. Now, what is going to happen during compression? When you're compressing the gas, the pressure increases, volume is going to decrease, so the heat energy is generated. Now this excess of heat energy increases the temperature. Same way, to keep the temperature a constant, now heat has to flow from the working substance to the surroundings. So this is what is basically an isothermal process. So in physics, when you're learning a thermodynamic system basically consists of cylinder piston arrangement with a working substance. And you can learn your isothermal process or adiabatic process, this thermodynamical process, using the system. Right, boys? So isothermal process is one in which the thermodynamic variable, pressure, volume can change, but temperature should remain a constant. For that, your system should be perfectly conducting to the surroundings. That's what I have here. Look at the statement. Pressure and volume of the system changes, but the temperature remains a constant. How can you make the temperature remain a constant? The walls of the container should be perfectly conducting to the surroundings so that heat is being exchanged between the system and the surrounding. And second one, during isothermal compression or expansion, the process should be very slow so that it provides sufficient time for the exchange of heat. So this is what is your isothermal process and the condition for your isothermal process. Fine, boys. Shall I go for deriving an expression for work done by the working substance in an isothermal process?
Sure, ma'am. And that's slow, right? Not low. Slow.
No.
Yes.
Slow. So just write the subheading. You want to write the statement for what? Do you need to write the statement for isothermal process, or will you refer your books? Will you refer your reference book, or should I give you time to complete it? I'm asking you, boys.
Complete the derivation, ma'am, or
Derivation, I will be with. I'll give you time. This slide, what I'm just now, the slide which is being shown to you. You want to write the statement, or it's fine for you?
ma'am, I took a screenshot, ma'am. You can continue.
Fine. No, listen, boys. Before we go this, what is that you are interested in? You are going to find the work done, like the heading was work done in an isothermal process. Ideal gas equation you have studied, right, boys? You have studied about the isothermal process, right? Okay, fine. Ideal gas equation. Now look at this. Suppose if I consider a cylinder piston, what happened, boys?
I did not want to flex this hard now.
Steve, your mic.
Steve, your mic.
Sorry, ma'am.
Now listen, boys. Suppose if I consider a cylinder piston arrangement with a working substance. Now let the initial pressure, initial volume and temperature of this working substance be equal to P1, V1 and T. So you have a working substance whose initial pressure, volume and temperature are respectively P1, V1 and T. Now you are going to supply heat energy, right boys? So now the gas is allowed to expand. The gas is going to allow to expand. Say the gas expands. The moment it starts expanding, it applies a force on the piston. The gas molecules will apply a force on the piston, and now the piston moves to a certain distance dx, so that the volume increases. This is increase in volume of the gaseous substance, that is your working substance. Are you clear, boys? So initially your working substance is at pressure P1, V1 and temperature T. You are supplying additional heat energy, external heat energy, so that the working substance undergo expansion. When it expands, right, it applies a force on the piston, moves the piston through a certain distance dx, so that its volume increases by a small amount dv. It's a very slow process. The first step, you need to find what is the work done by the working substance in increasing its volume by dV. So that is the first step. Work done by the working substance in increasing its volume by dV. Second step is what will be the total work done, so that the volume of the working substance changes to V2, pressure changes to P2, but temperature remains a constant. So the step one is nothing but you have to find what is the work done, so that the volume increases, work done by the substance, so that the volume of the substance increases by dV. The last step is what is the total work done by the working substance on the piston, so that its volume changes from V1 to V2. Are you clear, boys? 11B, are you clear?
Yes, ma'am.
Okay, fine. Now we'll start with that, boys. Right. So you are considering n moles of an ideal gas contained in a cylinder having conducting walls and provided with frictionless and movable piston as shown in the figure. So you can have a diagram. So this will be a piston cylinder arrangement. So working substance initially at volume V1, pressure P1, temperature is T. Now you are supplying heat energy. Heat energy is supplied so that the piston moves to a certain distance dx, and the volume increases by an amount dV. So let us find what is the work done in moving the piston through a distance dx or increasing the volume by an amount dV. Then later on we'll see what is the work done so that the volume increases to V2. Okay. Now we can go for this, boys. What is that? Work done by the gas when the piston moves up to a distance dx. So what is work done? Force into displacement. Force is what is force? Force is equal to pressure by area. So that you are applying over here. So this is dW is the work done in moving the piston to a distance dx so that the volume increases by dV. Up and down, boys. Still the boys haven't come back, boys. Come in.
No, ma'am, they joined back.
No, we're here, ma'am.
Shake. Yeah, there.
Here.
Yes, ma'am, they joined.
Fine. Copy down so that I'll go for the work done.
Ma'am, should we write in the diagram that heat energy is supplied with
No,
arrow?
that's not necessary, but you should understand, boys, because the substance is undergoing expansion, which means you are supplying heat energy.
All right, ma'am.
Kavin, can you answer? Kavin? Shall I go for the next one? So we have to find what is the total work done so that the volume increases from V1 to V2. For the next one, boys. Shall I go for the next slide?
Ma'am, could you repeat what you just said? Voice is breaking down.
No, I have to check what will be the work done in so that the volume of the working substance changes from initial volume V1 to final volume V2. You have to use your integration method of integration.
Ma'am,
Yes,
so force is pressure by area, right?
pressure is force upon area. So I wrote the other way.
Okay, ma'am. So then it's supposed to be
Yes, I think
P
so.
by
Yeah,
A,
just
right?
make correct. Just make that
Okay,
make
ma'am.
this. Fine. Now the question comes: what will be the work done? Suppose the gas expands isothermally from the initial state P1 V1 to the final state P2 V2. The total work done W will be equal to integral dW, so that the volume changes from V1 to V2. We are not concerned about pressure. We just take about V1 to V2. Because what we generally consider is that why not P1 to P2? When the displacement is very small, we'll just consider the force applied on the piston is almost, it's not a variable force, it is only a constant force. So that's the reason your pressure is not, the change in pressure is not be taken into consideration anyway. So this becomes equal to integral V1 to V2. What is dW? Can someone answer? Fadil, what is the expression we got for dW? Fadil, Dheeraj. Okay. Was
Ma'am, we
it
got
PdV? Okay, fine. P dV. Now mark this as equation 1. Now according to your gas equation, ideal gas equation, right? PV is equal to nRT because you have n moles of the gas, isn't it? Present here. So then what is P? P becomes equal to nRT divided by V. Clear was? Now you substitute 2 in 1. So substituting equation 2 in 1. Your total work done, W becomes equal to integral V1 to V2. Instead of P, I'm substituting it as nRT divided by V dV. Now look at this one. The number of moles of the gas remains a constant. R is Rydberg constant. Even R remains a constant. T is temperature. T remains a constant. Was N, R, T are all constant. They are all constants. So I'm just removing it outside the brackets. So it becomes nRT integral V1 to V2 dV divided by V. Now I have to evaluate this integral. Now what is generally dx by x? What is this was? What is dx by x? Log e base x. Haven't you learned this? Haven't you learned this?
And we haven't learned integration.
The other class. Okay, yeah. You haven't. Okay, anyway, boys. Dx by x. This is the rule, right? Dx by x is log e base x. So natural logarithm, you have to convert it to log 10 base. So anyway, W becomes equal to nRT log e base x, sorry, log e base v, because here the variable is v. V is changing from v1 to v2. This integration you haven't studied. Only differentiation is going on right now. You are using UV method. I saw I think last week. I saw in your mathematics class you were using VU dash plus UV dash.
Yes,
We
ma'am.
would differentiation, ma'am.
And that's
Differentiation.
differentiation.
Yeah, differentiation. Exponential powers also you use your exponential powers also under differentiation.
Yes, ma'am.
Yes. Yes.
Yes, I was watching the class. So integration is not being, still it has not come up to your syllabus,
No,
right?
ma'am.
Now what else to do was, now you have to assume. Right, boss? Just check. You need to assume this is log e base x. Now you have to convert it to log 10 base. Whatever logarithm we are using, it is log 10 base. Are you clear, boys? So now I have to convert e base log to 10 base log. For that, I have to multiply it with 2.303. So copy down. Only one more topic is left in this chapter. I think the last period I'll be able to complete. And tomorrow we'll start with kinetic theory of gases. Even there, only 3 topics are there for your exams. So most probably by tomorrow I'll be able to complete the entire chapter. Then once we'll go for your revision for your practicals. And then the regular theory revision will start. Complete this boss. W is equal to nRT log E base V, V1 to V2. Shall I go for the next one? Must let me complete and then I'll. It's only 3 more steps left behind.
All right.
Sure, ma'am.
This is how you convert can I write? Log E base x is equal to 2.303 log 10 base x. Log 10 base x is the one what we generally 10 base x. So that E base x I have converted to 2. Log 10 base. Fine boys. So I have to use the v takes the upper limit first and then v takes the lower limit next. So you know that log was, have you studied about this? Log a minus log b. What is that? Log of a by b. Log a minus log b. Okay. This is also an identity. Boys, here I am using v takes the upper value first. Log 10 base v is going to take upper value v2 first. Log 10 base v2, then v is going to take the lower value v1. So here I am using this identity. So this is the work done in an isothermal process. Those who have completed can leave for your other class. Thank you.
Thank you, ma'am.
Thank you, boys.
Thank you, ma'am.
Thank you, boys.
Thank you.
Thank you, ma'am.
Thank you, boys.
Thank you, ma'am.
Thank you.
Thank you, ma'am.
Thank you, ma'am.